Welcome everyone to the Spectral Geometry in the Clouds seminar. As you saw, this meeting is recorded, so you are warned that this is recorded. And today we have the pleasure of having Jared Wunsch from Northwestern University, who will speak about semiclassical analysis and the convergence of the finite element method. Jared, the floor is yours.
Okay, thank you. I'd like to begin by thanking Jean and Alexandre very much for this invitation and for running this seminar, which has been one of the real lifelines, mathematical lifelines for me in these hard times to sort of feel I'm still connected to the research community. So it's an honor to be able to talk. I'm going to talk on some joint work with David Lafontaine and Euan Spence, both at University of Bath. This is part of a sort of a long-term ongoing project I've had with these guys. It started with just Euan in applying methods of semi-classical analysis to problems in the numerical analysis of the high-frequency Helmholtz equation, which is somehow manifestly the same problem we study in semi-classical analysis, but where there are where I think it's been historically true that phase space methods haven't been much used, and so there are a lot of interesting new applications of microlocal analysis there. I will remark that there are a number of heavy-hitting microlocal analysts in the audience, and this is not a heavy-hitting microlocal analysis talk. This is a talk on by and large uses of existing methods in novel places. So a lot of the beginning, in fact, is going to be just about numerical analysis, which was somehow the novelty for me, and there are probably some numerical analysts out there too, to whom I apologize also, that you'll know everything I will tell you in the first half of this talk, and possibly more. So the talk is on the Helmholtz equation, the high-frequency Helmholtz equation. So to begin with, let's pose it just in RD, flat RD, let's say, Laplacian plus k squared u equals f. F will always be compactly supported for simplicity, and it'll be L2. So this is time-harmonic solutions to the wave equation. This is the domain of stationary scattering theory. So imagine we're working in free space, or in the moment in an exterior of an obstacle. The goal is to study solutions numerically, to actually produce computations of solutions with a given f. And we're going to be interested in what happens as k gets large. We want somehow uniform understanding in how to solve this numerically for large values of k. So there are, of course, many solutions to the equation I wrote at the top. So to make this unique, we're going to use the Sommerfeld radiation condition. This is the condition that the solution be in some sense outgoing near infinity. It looks approximately like an outgoing spherical wave if you're far enough from the origin. If you're more used to scattering theory, this is what you get when you take the limit of the resolvent from the upper half space. So this is what you get when you study, if you like, forward solutions to the time-dependent wave equation, but in frequency space. And so I wrote it on the previous slide as if it were just in flat space, but actually we're going to be interested in various complications. So to begin with, let's say inhomogeneous anisotropic media, we could have a coefficient matrix A that measures the anisotropy and a variable sound speed, but they're going to be respectively identity and 1 near infinity. So there's some compact interaction region where interesting stuff is going on. Or for the purposes of this audience, presumably it would have been more efficient for me to say, let's take the Laplace-Beltrami operator with respect to a Riemannian metric that is Euclidean outside a compact set. And it's fine to just think of that. We will want to talk about obstacles. In this talk, it'll be only Dirichlet boundary conditions, although Neumann is interesting too. And so you could say have an obstacle with variable coefficients in the exterior. And I won't really have time to talk much about this, but there are also interesting results in this direction dealing with transmission problems or penetrable obstacles, if you like, where your coefficients have a jump across an interface and you have appropriate matching conditions across that interface. I phrased the problem, the basic problem, as the inhomogeneous Helmholtz equation, but maybe more interesting actually from the point of view of practical applications would be the scattering problem where I have f equals 0, but what I'm really trying to do is solve where I have a solution that's equal to a given incident field plus an outgoing scattered field. These two problems are closely related, so I'll just stick to the one that I stated, but there's sort of equivalence for the scattering problem if you prefer, say plane wave scattering. And the pictures I'll show you are essentially plane wave scattering. So here's one. So this is the problem we want to solve. The question I want to address at the beginning of the talk is, how do we make these pictures? We is in large quotation marks because I've never made such a picture in my life. The interesting thing has been talking to the people who do. So this is supposed to be a plane wave scattered by these two obstacles here. Okay, and you can see there's interesting interference patterns, diffraction effects, all kinds of good stuff. So, to begin with, I'll introduce the computational setup. We reformulate the problem as a weak problem or a variational problem. This is familiar if you've ever thought about these solutions distribution theoretically. You're going to think about the solutions as weak solutions. So we integrate by parts by pairing the solution with some guy v. Okay, we integrate by parts, and the Helmholtz operator gives me these terms. And then we'd like to replace what's in effect an infinite problem on the whole plane with a problem on a compact set so we can actually do something on a computer. And so this is now done just on the ball. And we've finessed the Sommerfeld radiation condition in the following way. And this is sort of interesting, but not the main subject of this talk. So I don't want to say too much about it. So take the large ball and then solve the exterior problem on that large ball that says you want an outgoing solution to the Helmholtz equation, outgoing in the sense, again, of Sommerfeld radiation condition, and that's uniquely specified, and there's a Dirichlet-Neumann operator for that. So this dTn sub k takes the Dirichlet data on this large sphere to the Neumann data on this large sphere for the exterior scattering problem on that large sphere. That's entirely explicit in terms of Bessel functions. Not exactly a simple thing, but a computable thing, and something that you would, in effect, compute the integral kernel of once. So this is going to be built into our quadratic form in this formulation, and having it enforces that boundary condition. A different interesting talk, I think, is on the fact that that's not super computationally efficient to have to compute with that thing, and people sometimes substitute different things for that as kind of simpler proxies. But we'll just take it to be given that this is the exact thing, and this enforces the boundary condition at infinity. It's not self-adjoint is an important thing to keep in mind if you've ever thought about this. We've introduced some kind of asymmetry, of course, by having this outgoing condition, the Sommerfeld radiation condition, and that issue will become important later. Okay, so what's the weak formulation of this problem? With that preamble, it's just that for every test function v, we should have the pairing, the pairing of u with v with respect to its quadratic form is given by the L2 pairing of the inhomogeneity with v. And now it's all happening on a compact ball. Okay, so how do we compute? Well, we're going to use the Galerkin method, which is to say we take, instead of H1, we take a finite dimensional subspace of H1. I'll call it Vn. You should think that we're going to have a sequence of these. N is going to go to infinity, and they're going to get bigger and bigger and bigger, these subspaces. And instead of posing this weak formulation on the whole of H1, we just pose it on this finite dimensional subspace of H1. So we asked for a Un in this subspace, so that whenever I pair with Vn in this subspace, I get the corresponding right-hand side. So it's a finite dimensional version of this infinite dimensional weak formulation.
Jared, may I ask a question?
Please, Lenny, yes.
And what about the Dirichlet-Neumann operator from the inside?
From the inside.
You integrate by parts inside of the ball. So
right. So but there's going to be a Dirichlet boundary condition, let's say. So that part's okay.
Okay, so you put Dirichlet.
So if there's an obstacle, so there's two things.
Okay, thank you.
Yeah, thanks for asking.
No, I'm talking about the boundary of the ball.
The boundary of the ball. Oh, I see. No, but this is
inside of the boundary of the ball, not of the obstacle.
Oh, I see. Yeah, no. So this is just a replacement for the Sommerfeld radiation condition, right? So it's just saying that the solution on the outside is the outside. Is the outgoing solution that matches matches the Dirichlet data that's hit it.
Yeah, but when you integrate over the ball itself, you integrate by parts. So
right.
You're going to get a boundary term. Isn't it be a Dirichlet, the interior Dirichlet operator?
Well, you want it to be the one that's gonna. So no. I claim it's the exterior. I can try to
It's
do
just exterior, so no
just,
interior.
just the exterior one for the scattering problem.
Okay,
Yeah.
okay.
And there's nothing happens at the obstacle because there was a Dirichlet condition
Yeah,
there.
yeah, I
But,
understand.
but this is so. So by the way, what people sometimes do, of course, is to replace this with some approximation where instead you would take an impedance boundary condition, which is like an approximation to the Dirichlet de Norman condition, and that has the effect of absorbing some but not all of the incident wave. This takes it all. Alternatively, you could do complex scaling, okay, and that would be a fancier answer, and it works pretty well.
Okay, okay.
So how do we make the subspaces? Okay, and there are of course choices in how we take these subspaces, and the most common thing to do is to triangulate the domain. So we've got the exterior of some obstacle inside a ball. We triangulate it in some uniform way, where the triangles are of size of order h. It's unfortunate for us semi-classical analysts that this is the standard notation in the numerical literature. H is the triangle size. And we let the v sub n be piecewise polynomials in H1, I should add, of degree p on these triangles. We fit them together so that they're in H1. And so we get a finite dimensional space from these piecewise polynomials. And if you apply the Galerkin method with this choice of the subspaces of H1, that's the finite element method. Okay? So how do you make the finite element method work? How do you try to converge to an approximate solution to get a good picture? Well, you actually have a couple of options, but to begin with, let me talk about the simplest formulation. You refine the triangulation. You decrease the mesh size h. So this is called HPFEM as a result. So you're going to fix the polynomial degree. You can take that to be degree 1 for now. Piecewise linear is already pretty good. In figuring out how much work this is going to be, it's instructive to count the number of degrees of freedom, and it turns out you get p over h to the d if you do that arithmetic. Okay. So now we want to know, does this work? Expect success in doing this. And there are a couple of different measures of whether you should expect success, and I'm going to focus on one fairly simple-minded one, which is called quasi-optimality, and that's the following. We've got these subspaces of H1. They're supposed to be increasing to fill out H1. In each given subspace of H1, there's some closest point to the actual solution, which of course we don't know in practice. So the Galerkin method is not going to pick out that closest solution. Why would it? We would just want to know that it does comparably well, in the sense that it picks out something that's no farther than a fixed multiple from of the distance from this subspace to the actual solution. So it doesn't do any worse than a constant multiple of the optimal thing in the Galerkin subspace. Okay, that's quasi-optimality. And the tricky thing is you want this estimate in a way that deals uniformly with what happens as k goes to infinity. You want to know, given a k, if you like, how do you pick h, the mesh size, to guarantee quasi-optimality? That's the game. You might object that this isn't really what you want to know. What you really want to know is where the right-hand side is just f, in effect. You just want to know how far you are from the actual solution. And you can upgrade this estimate to that estimate. That's called a relative error estimate in many circumstances. But in some sense, the more fundamental thing is quasi-optimality here. So it's known, for example, through work starting with Ihlenberg-Babushka a long time ago now, that if p equals 1, say, you can guarantee quasi-optimality under this condition. So this is a uniform condition in k. It says that h, the mesh size, times k squared, the square of the wave number, should be sufficiently small, bounded above by some constant. Now, in terms of degrees of freedom, that means you've got k to the 2d degrees of freedom. So it's rather a lot if you're in 3D, say, k to the 6th degrees of freedom as k goes to infinity. And so you might ask, can you do better? You'd like very much to do better. And if you think about it just from the point of view of what do these solutions look like, you're very tempted to think you should be able to get down to k inverse, because after all, a plane wave of frequency k is oscillating on a scale 1 over k. And so if I triangulate so that, I'm like 1/1000th of that in my mesh size, surely I can resolve these plane wave oscillations well. Interestingly, fascinatingly, that's not true. So this is a very famous paper of Ihlenberg and Babushka on what they call the pollution effect. It's the observation that even in one dimension, for the most simple-minded problem you could pose, quasi-optimality fails on this scale. It's the pollution effect. And the numerical analysis community is very interested in this. This paper has 750 citations. So it's considered a big deal what to do about the pollution effect. So
sorry, Jared, is it clear that this pollution effect carries on as you augment the dimension? That it's not only
paper or in very soon after subsequent ones. It gets worse, actually.
Oh, okay.
They in fact point out there's some ways around it in one dimension, but even those fail miserably as soon as you go to higher dimensions. So it's actually only worse. Yeah.
Okay.
So there are ways around this though, and one of the most famous is to change your method ever so slightly. So here's the strategy now. Instead of just improving our approximation by decreasing the mesh size, we're simultaneously going to increase the polynomial degree as k goes to infinity. Now, so here's what we do. This is called HPFEM, where we both decrease the mesh size and increase the polynomial degree, which I remind you is called p. That's the degree of the polynomials we're using. So Malenk and Sauter showed that in certain cases we do recover quasi-optimality if we increase p just very mildly, and then all we have to do is keep hk over p sufficiently small. So remember, it was hk squared that concerned me in one dimension. So we've replaced the k squared with a k. You recover k to the d degrees of freedom now. So it's very efficient. And p is only increasing rather modestly. Okay, my sometime collaborator Maciek Zworsky likes to say that for the purposes of numerics, log is a constant function. So this is no big deal. P increases like the log. I'm told that in practice, I mean, they get to p equals 10 or something. It's actually fairly modest sized. So this is this theorem of Malenk and Sauter. It's very important that you can get down to this much smaller number of degrees of freedom, but they are only able to show this in certain cases. So free flat space, that works. That's one case. And the other is more serious. It's the exterior to an analytic obstacle or a polygon with Dirichlet boundary conditions where there's a polynomial resolvent estimate. Okay, I'll say more about polynomial resolvent estimates at the end of the talk. So this is what I mean by a polynomial resolvent estimate, polynomial in the wave number. And crucially, constant coefficient operator. You can't have variable media. Okay. So I said I'd say more about polynomial resolvent estimates. For now, if you're not familiar with them, assume the obstacle's non-trapping, which is to say that any billiard trajectory escapes to infinity in the exterior of that obstacle. That's certainly a case where you would have such a thing. Okay. So the theorems I want to talk about are generalizations of this theorem of Malenk and Sauter that show that you recover this quasi-optimality in a much broader setting under appropriate conditions. So we can have C infinity variable coefficients and no obstacle, okay, with the exact same theorem of Malenk and Sauter then. So hk over p sufficiently small and p growing logarithmically gives you quasi-optimality. Or you can have the same setup where you have an analytic obstacle enjoying polynomial resolvent estimates. There should be analytic coefficients near the obstacle for your wave equation, for your Laplacian. And we have quasi-optimality under these conditions, which are almost the same. Malenk and Sauter have a 1 over p there. Okay, so it's a little better. And correspondingly, we lose a log. We have ever so slightly more degrees of freedom. Okay. We also have related results for transparent obstacles that I won't talk about because they're not as strong. They're more of interest in HPFEM, where you pick a large P and fix it. Okay, any questions before I proceed? All right, I'll go on.
I have a naive question. There are some implicit constants in your here, and they are depending on the domain which you use to compute.
Yeah, right? Yeah. I don't have great control in terms of the domain. You'll see that the way the domain enters is a little bit subtle in the end. So yeah, they would definitely depend on the domain in subtle ways that I'm not sure I can quantify. I would remark also that it has always made me very suspicious that there should be a theorem in numerical analysis with analyticity assumptions, and I find that somehow very amusing. But you'll see naturally how this arises in practice. There should be a Gevrey theorem probably, but I don't know that there's much audience for that theorem, so I haven't looked into it.
There may be. Just to be clear, the mesh is triangular, yes? Not
the mesh is triangular, yeah.
Okay,
yeah.
thank you.
But I'm not going to talk much about how the mesh enters. In the end, we need some sort of black box about how well things on triangular meshes can approximate things where you have derivative estimates. So it's not really going to arise in my talk per se.
Yeah, thank you.
Sure, thank you. Okay, so I don't have long enough in an hour talk to explain every step and how proving this theorem reduces to the estimates I'm going to show you. So I'm going to have to skip some parts in the middle about about why we need to prove the estimates we need to prove. But let me tell you some of the ingredients here. And the main ingredient is an estimate on an adjoint problem. Remember, I said this was not a self-adjoint problem once you've introduced the Sommerfeld radiation condition, this exterior Dirichlet-Neumann map, if you like, on the sphere. It's not self-adjoint. But the adjoint problem is essentially the same as the original one. It's just that you've complex conjugated. Okay, so you've switched the outgoing Sommerfeld radiation condition to the incoming Sommerfeld radiation condition. But it's the adjoint problem technically on which you need estimates, just as you would in proving an existence theorem in PDE. Right, an estimate on the adjoint problem can give you an existence theorem. So I'm going to let S star denote the solution operator to the adjoint problem. S star of the right-hand side is the solution to Helmholtz that is incoming rather than outgoing. But for all practical purposes, this is the same as our original problem. It's just a complex conjugate. The crucial ingredient is an estimate on this so-called adjoint approximability constant. So what does this say? You solve the adjoint problem for data in L2, okay? You take the closest point in your Galerkin subspace, okay? Now I really mean the closest. You just see how well your Galerkin subspace approximates that thing. You divide by the norm of the data, and that the worst constant there is what we're calling eta of the Galerkin subspace. So it says, how well can you approximate a solution to the adjoint problem in the Galerkin subspace? Certainly, it seems important to know this, okay? It just sort of tells you something about how these Galerkin subspaces are filling out H1, and also something about how bad the solution to the adjoint problem is. The norm here, this H1 norm, is a weighted norm. It's got a k squared on the L2 part. If you like, it's a rescaled semiclassical Sobolev space. That probably means something to most people in this audience. So the claim is quasi-optimality follows if k eta is sufficiently small. So eta should be going to 0 like 1 over k as k is going to infinity. This is a famous argument due to Schatz in 1974. I have one very dense slide on it, and I can explain it if people really, really want, but it's going to take me a while. So I've put it at the end just in case there's high demand. I'm going to skip it, okay? It's a beautiful argument, just sort of a weak formulation kind of argument in a very clever way. So, okay, sorry. So the game now, I claim, is this eta. It's to produce good estimates on eta. So how are we going to do that? So the thing I'm not going to tell you, partly because I don't really know very much about it myself, is how good an approximation do I get in my Galerkin subspace if I create it this way to something in H1. Okay, and so this is where there's a little bit of a black box. So I could get a good approximation for two different reasons. S star of f could be small in H1. That would certainly do. Thing one. Thing two would be S star of f could have very good estimates on very high derivatives, because then increasing p will somehow benefit me, right? If I have something where I have very good derivative estimates, then approximating it by very high degree polynomials should work well. Okay, so these are estimates proved by Malenkin-Sauter. They're a black box for us. So the game of Malenkin-Sauter is to split U, the solution to the adjoint problem, into two pieces, which they call the analytic piece and the H2 piece. And they each have separate virtues that make for good adjoint approximability. what's the virtue of the analytic piece? Well, it is, as I say, analytic. Again, seems crazy from the point of view of numerical analysis, but remember now, we're letting some polynomial degree go to infinity, and we're approximating by higher and higher degree polynomials, and so you can start to see how this might come in. So it's supposed to be analytic and enjoy Cauchy estimates that are appropriately uniform in the wave number. So they grow like k to the alpha if I'm taking alpha derivatives, okay, in addition to the usual kind of Cauchy estimate growth. And then we're allowing polynomial growth in k as well. That's fairly minor. What about the H2 part? So it enjoys a different estimate. It just enjoys H2 estimates that are uniform in k with this behavior. So let me isolate not the H2 one, but the L2 one. If I don't take any derivatives, I get k to the minus 2 times the L2 norm. So if you know about resolvent estimates, and if you don't, you'll know more by the end of this talk, you'll recognize that that's a power of k better than you deserve for estimating u in terms of f. So somehow this piece is just plain smaller. Okay, so you should think it's not particularly smooth, but it's smaller than u overall as k goes to infinity. So again, two pieces. One of them has very good high derivative behavior. The other is small. That allows for good adjoint approximability. So the game is about the splitting. And so what we introduced to this problem was a new strategy for splitting, and it works very generally. In fact, you could take the setup of Shostron-Zworsky style black box scattering. We can tell you how to do this splitting. We can't in general tell you that these pieces satisfy the good estimates. That requires more. But it's in some sense very simple-minded, I would say, as you'll see in a moment. So how do we do the splitting? We use the functional calculus for the operator we're using. Okay, we're going to use that to split the thing. So now I have to become a semi-classical analyst again. So since h is already taken, h bar is a semi-classical parameter. H bar is 1 over k. Okay, and I'm going to use the functional calculus for h bar squared Laplacian, the self-adjoint operator. So my equation reads h bar squared Laplacian plus 1u equals, whoops, there's an h bar squared missing there, h bar squared f. And I'm gonna split u in the following way. So I take a cutoff function that I'll call chi sub l, and chi sub l just is supported in some big window out to approximately size lambda, capital lambda. Okay, and so that's the low frequency part. Chi sub l is 1 on that big window, and chi sub h for high is the high frequency part, is 1 minus that. And I pick a spatial localizer also. Okay. That's this phi. And so here's how my splitting goes. I localize u by multiplying by phi, and I split it into the low frequency part and the high frequency part just by using the functional calculus. Okay, that's all. So I'm roughly splitting into frequencies above and below capital lambda times k, where lambda is this parameter in the definition of my cutoff function, and k is the wave number. So think of lambda as being fixed and big. It's like 10 or something. So why do these pieces enjoy these estimates? So let me start with the analytic part, the allegedly analytic part. What would happen if we were in free space? So in free space with the flat Laplacian, what is this doing? I'm using the functional calculus for h bar squared times the flat Laplacian. So that's to say Fourier multipliers. So this analytic part is obtained by localizing u, Fourier transforming, and then multiplying by a cutoff in frequency space, and then inverse Fourier transforming. Okay, so of course it's analytic. So that's all good. Moreover, when I differentiate on the Fourier side, that's like multiplying by xi, by powers of xi. Well, the cutoff ensures that xi is less than capital lambda k, and so I pull down capital lambda k times the number of derivatives if I want an estimate. I do need an L2 estimate on the right-hand side here, and so this is the first of several places where I will remark that we do need some kind of resolvent estimate. Okay, I would like this to be bounded in terms of f a priori in some reasonable way, so I'm going to assume that I have this polynomial resolvent estimate. Again, more on that later. Okay, so in flat space, this thing is analytic and satisfies fantastic estimates. So, but what happens more generally? What about general coefficients or obstacles? So how do we get analyticity from the functional calculus? This actually is maybe my biggest question to you, the audience, because it's possible somebody here has a better idea than I do of how to do this. So the best we can do is the following. So remember, I've cut off to a compact window in the spectrum of the Laplacian, and I want to say, why am I analytic? Okay, well, the boundary, I've got an analytic obstacle and an analytic coefficients, let's say, and what I'm going to do is just observe that since I'm compactly supported in the spectrum of the Laplacian, I can run the heat equation backwards. Okay, I took chi L of my operator. Well, e to the t times lambda times chi L of lambda is a bounded function. And so I get a bounded operator on L2. And so when I apply this thing to phi u, I get an L2 estimate. And so if you like, I can turn this around and I can say that UA itself is in the range of the forward heat flow on L2 for time th bar squared. Okay. And there are beautiful analytic estimates due to Escariaza, Montaner, and Zhang, surprisingly recent, I discovered, that say, we know that the heat equation makes things analytic in nice situations, but they have uniform estimates for small time on how analytic, if you like. How do the Cauchy estimates deteriorate as the time for the heat flow goes to zero? Well, if you've got an analytic obstacle and analytic coefficients, they have these estimates. This is where we have to limit to Dirichlet boundary conditions, because I don't know this theorem for Neumann boundary conditions. And this is where we get into trouble with partially transparent obstacles, because I don't know this theorem for partially transparent obstacles. If anyone knows references, I would love to have them. Okay, but in this boundary case, at least with Dirichlet conditions, this gives us our desired analyticity estimates for this part. All right, how about the H2 part? So it might have been better to call them low and high frequency parts. So that was the low frequency part. Low meaning less than a multiple of k. This is the high frequency part. So first, let me observe that the equation satisfied was h bar squared Laplacian plus 1 u is h bar squared f. So if I can just apply the cutoff to both sides of that equation, the spectral cutoff to high frequencies, it commutes, and I find that this high frequency part satisfies this nice equation. And now look, the high frequency part, well, it lives at high frequency, okay, chi high of s. 1 over 1 minus s, which is the function of the Laplacian, of h squared Laplacian I'm taking here, is bounded on that. I've just cut off away from where that multiplier was 0. Okay, so I can divide by 1 over 1 minus s. I can divide by 1 minus s, that's to say. So I can invert that operator. It's like elliptic regularity, but the cheapest elliptic regularity ever. I'm just using the functional calculus, right? So I can invert this thing. This is it has a bounded inverse on the range of this, and I just get this estimate where I've gained an h bar squared. And that was my estimate. That was my H2 estimate. It's just ellipticity. Except I cheated. So I cheated, of course, because U is definitely not compactly supported, and I didn't have a cutoff in there. So I do need to insert a cutoff. That has the feel of some annoying technicality, but this is really not an elliptic problem, right? For high frequency, the Helmholtz equation you should think of more as a hyperbolic operator than an elliptic one. There's propagation. You can't just go and localize your estimates because you have big errors in general. So I have to put in a cutoff phi to make this argument work. So remember, really UH2 was this spectral cutoff applied to localized U. And I end up with some rather tricky commutator terms in trying to move these things across the phi. So in particular, I'm interested in the cutoff, the commutator of the spectral cutoff with the position localizer phi, because this phi u doesn't really satisfy my equation. So here's where we need to know more about the functional calculus. So it's a theorem of Helfer-Robert that if I have a compact smooth manifold, say, and I take a function of h bar squared Laplacian, I get a pseudo-differential operator. Okay, and then there's this beautiful Helfer-Sjöstrand construction of the functional calculus that gives a new proof of that. It's a little later. That tells you the following thing. I think this is actually in a paper of Sjostrom stated in this form, that if I have anything going on inside of my black box, I have some obstacle, some partially transparent obstacle, some thing with corners, something horrible. Away from that, it's still true that the functions of my operator are pseudo-differential. Okay, so everything localizes. So if I stay away from the obstacle, I'm still getting a pseudo-differential operator, modulo negligible errors. So this commutator I want is really a commutator of pseudo-differential operators, because phi was supposed to be 1 near the obstacle. It's just cutting off away from it. So it's a commutator of pseudo-differential operators, and I know how to deal with commutators of pseudo-differential operators. I get another pseudo-differential operator. And I know where it's micro-supported, where the symbol is supported. It lives where the cutoff had non-zero gradient, that's to say in some big annulus. And where xi, the phase variable, is bigger than lambda minus 1, because that's where this spectral cutoff lived. Okay. On the other hand, that's in the elliptic set of h squared Laplacian plus 1. It's exactly the same argument as on the previous slide, which was phrased in terms of the functional calculus, except now it's in terms of the pseudo-differential calculus, that we're living in phase space where this thing is invertible. So elliptic regularity tells me that I can estimate this commutator term by the right-hand side f plus an error, which I will again estimate by having a resolvent estimate. So I should remark here, actually, that this is where we can do better in the case of C infinity coefficients. So I've mainly structured this talk to be about the obstacle problem. But if you have C infinity coefficients, you can actually do something in a way even more naive. You can just use a Fourier multiplier to do your decomposition, high frequency, low frequency. Just ignore the coefficients, and then the pseudo-differential calculus saves you in dealing with the fact that the spectral cutoff doesn't commute with the operator that you're using, because you know all the errors are micro-supported in places where h squared Laplacian plus 1 was elliptic. And so that's where we can do better. And in the C infinity coefficients case with no obstacle, we can match the original hypotheses of Melenk and Sauter. So let me now turn to the final part of the talk on resolvent estimates. A number of people in the audience are experts on these. So I'm going to begin by telling you things you already know. I've switched back to non-semiclassical notation. So I'm going to talk about dealing with remainder terms like this, for instance, that were on the previous slide, phrased in terms of h bar. I have these L2 remainder terms. There should have probably have been a phi here, though, otherwise we'd have been in trouble. Some cutoff. So I have error terms in U that depend locally on the L2 norm of U, and there are k to the minus infinity multipliers out front. That's fine as long as I know that phi u has a polynomial bound in terms of f, the right-hand side. But it's known that this doesn't always hold. So here's a trapping obstacle, one in which there are rays that bounce around forever and don't escape to infinity, many of them in fact. And it's known that in these cases, in general, you do much, much worse. So it's a famous theorem of Nicolas Burck that you do still have some estimate. You have an exponential estimate. It's easy to see in many explicit examples that you don't do any better than that. You could take a sphere glued into a plane and then take a sequence of spherical harmonics localizing along an equator and just cut them off locally. You make an exponential small error in doing that. You have very good quasi-modes. And there's, for example, a paper of Cardozo-Popov where they showed that in very general settings where you have sort of strongly trapped trajectories, you should expect estimates that are not much better than this. They have lower bounds that are quite close. So the good situation, as I referred to at the beginning, is if there are no trapped trajectories, if every billiard trajectory or geodesic more generally escapes to infinity, the optimal estimate is this. Remember, with a 1 over k squared, that was the estimate on my h2 term. So that was better than you could expect even in Euclidean space. This is what you get in Euclidean space and what you would get if there are no trapped trajectories. That's a famous theorem to which many people have contributed. It has a long and glorious history. because of the complications of propagation of singularities on manifold boundary. So that would certainly suffice to deal with our error estimates. It's known in the work of many authors, starting with Ikawa, that if I have very mild trapping, such as you would get from a trajectory bouncing back and forth between two convex obstacles that are probably supposed to be separated more than I've just drawn them, that you do get estimates with a very small loss. There's just a logarithmic loss. And Hans Christiansen and I showed a few years ago that there's a sort of a family of situations where you have a kind of a degenerate hyperbolic trapping. If you sort of flatten these sides in some polynomial way, you could get various polynomial losses, various polynomials in K on the right-hand side. So there are certainly many situations where you get polynomial resolvent estimates, but the general case of a trapping obstacle is very bad. Okay, but I want to end by saying that actually, somewhat surprisingly, most of the time you don't care. So I entitled the slide "Polynomial Resolvent Estimates Always Mostly Hold." So this is a theorem that came as a surprise to me and was an interesting example of a theorem in sort of pure scattering theory that I, as a semi-classical analyst or scattering theorist, would never have conjectured if it hadn't been brought to my attention by colleagues in numerics. It says the following. This is a theorem Lafontaine, Spence, and I proved in 2019. No matter what you've got, so imagine a horribly trapping obstacle, your least favorite, or a partially transparent obstacle, no matter what's in the black box, and it is phrased in terms of black box scattering theory, you've always got a polynomial estimate with a power essentially 5d over 2. D is the dimension. It always holds. All you have to do is exclude an arbitrarily small set of frequencies. So why would we have imagined this might be true? Because, as I say, it surprised me. Yves Capdebask had analyzed the situation where you have a penetrable ball. You've got a ball in 2 or 3 dimensions with constant wave speed inside and outside, just the standard flat Laplacian, just with a constant conformal change, and you rig it so there's trapping, right? So you've got trapped. You've got total internal reflection, so there are trapped rays from the point of view of the propagation of singularities. So this is one of these situations where you expect very bad estimates, and indeed you can show that there are lots of resonances close to the real axis that you shouldn't have, and you shouldn't have better than an exponential estimate. But Capdebask showed this, and indeed showed it with a better exponent here by a sort of a bravura Bessel function computation. So we started discussing this, and initially, as somebody who was brought up in the study of resonances, I thought, can't possibly be true. There's resonances exponentially close to the real axis. But eventually we realized this was right, and we proved this theorem. And then quite recently we discovered that, in fact, in old work of Stefanov, there's a very similar theorem, not sort of phrased in quite this language, but awfully close. So at least Plamen, I think, morally knew this. So here's another piece of evidence for this theorem, and another reason why we thought it might be true. It's kind of a remarkable picture. So this is a picture from Euan and Spence of a scattered wave from a plane wave, and it's incident on a partially transparent obstacle. So this is a situation of Capdebask. So there's supposed to be trapping from the change in sound speeds, and they're at slightly different frequencies. These pictures. They differ in the last significant figure. Okay. So what I want to draw your attention to is the scales, and I'll zoom in so you can see them better. This one goes up to 2. This one goes up to 3,000. So by changing the frequency in this last significant figure, I won't even try to count what power of 10 that is. I don't know how far out it is. Really small. I've made this enormous qualitative change in the size of this trapped thing. Essentially, it's telling you that the resonance width is really incredibly narrow. Okay, so there is indeed a resonance very close to the real axis with this as the real part as a real part of the resonance. This is the resonant frequency, but it's really narrow, and being ever so slightly away from this bad frequency gives me a much better estimate. So what are the ingredients? So why could this theorem be true? And once I tell you the ingredients, you can go home and prove this theorem. There's, again, not that much that's novel from the point of view of microlocal analysis. The tools were available. So as I say, the reason not to believe this theorem is that the resolvent blows up at these resonances in the lower half plane, which should be exponentially close to the real axis in bad cases like this. And this should be very bad for us. But there are only polynomially many resonances in, say, a strip near the real axis in quite great generality. So this is theorems of Sjöstrand and Zworsky and Vodev, for instance. So there's only polynomially many bad frequencies. And there are exponential bounds on the resolvent away from the resonances. You can find these in a paper of Tang-Zworsky. And so indeed, in the same paper of Tang-Zworsky, they show you how to use the semi-classical maximum principle, which is essentially a kind of a semi-classically quantitative version of the three lines theorem. In this case, they're not full lines. You have to truncate to a box, so it's a little trickier. So think a long, narrow box. In a long, narrow box near the real axis, you can approximately use the three lines theorem. Imagine a box like this, but getting very narrow in comparison to its width. Its width is comparable to some power of h. So you have a good estimate for the resolvent in the upper half plane because it's the resolvent of an actual self-adjoint operator. It has, you know, a 1 over the imaginary part kind of behavior, so it's not so bad. It is getting singular at the real axis. And in the lower half plane, well, it's very bad indeed at the resonances, but as long as you stay away from the resonances, you know something. So you can use the semi-classical maximum principle to interpolate between these two estimates, and you get an estimate on the real axis. And as long as you stay just, you know, sufficiently away from these polynomially many bad points, you get at worst a polynomial answer. And the polynomial answer we were able to get was this 5d over 2 plus epsilon. It's probably not optimal. We were able to do a little better if, for example, you assume that the resonances cluster a little bit. So we really wanted to recapture Kaptebask's numerology for the ball. The ball, of course, has this symmetry. The resonances have multiplicity. So actually, there are fewer points that you need to stay away from because the resonances are all sort of lumped together. So there's fewer bad places in the lower half plane. So that helps your estimate. And we were able to do a little better as a result of that, but not as well as Kaptebask. So I still don't know what the optimal polynomial growth is in that theorem. It seemed a little bit hard to perfect it. So actually I've been talking too fast, obviously. I'm now done, and so I will take questions.
Thank you very much for this talk. We have definitely some time for questions, so you can unmute yourself or ask the question in chat if you want. I mean, I have a question myself. I mean, as soon as you said that you had a good explanation for Schatz' argument, I was immediately quite interested about that because it is the kind of thing that I find really.
All right, you asked for it.
Yeah. No, I mean, and I'm already happy seeing that slide.
Okay. Should I take another short question first, or shall I plunge right in? I can sort of take you through this slide. It's very pretty. It's not quite a logically complete argument. Why don't I just do it? I'll do it reasonably quickly. So this is the Schatz argument. So you let U be the solution, and UN is the Galerkin approximation. So the first thing to notice is that if U satisfies a variational problem or a weak problem, and UN does too. So you subtract those two facts. So U paired with VN is FVN, and so is UN paired with it. So you get this Galerkin orthogonality, that if you take the difference of the actual solution and the Galerkin solution, they're orthogonal to everything in the Galerkin subspace with respect to this non-Hermitian A. Okay, it's not totally obvious. This thing's non-Hermitian, right? So, okay, so now let's let F be the best approximation, let Fn be the best approximation to the solution to the adjoint problem with U minus UN as my right-hand side. So I solve this adjoint problem. And so the point is that if I plug the solution to this adjoint problem into my quadratic form, essentially by definition, that's the L2 norm squared of U minus UN. That's the thing I'm trying to get at. That's what it means to solve the adjoint problem, right? Integration by parts would have put the original operator here. It puts the adjoint operator on that side if I want to move it there. Okay. So u minus un squared is given by this pairing with respect to A. Now, by Galerkin orthogonality, I can subtract off Fn here. Okay, this is the best approximation to this thing in the Galerkin subspace. Okay, so I get this. And this is the thing I know how to estimate in terms of eta. That's what eta is telling me about, right? So so A is bounded in the H1k norm on both of the pieces, right? It involves a gradient and a k times the L2 norm. And that's what H1k is about. So by definition, this right-hand side is bounded by eta times the H1k norm of this piece times the L2 norm of u minus un. And so I can divide through by the L2 norm of u minus un. And I get u minus un in L2, no subscript means L2, is bounded by eta u minus un H1k. And eta's going to 0 fast, right? So eta is like 1 over k. It's a lot smaller than 1 over k. So I remind you, the H1k norm is the norm of the gradient of u squared plus k squared, the norm of u squared. Okay. So this says that the L2 piece is much less than the gradient piece. That's exactly what this is saying. Okay. So the point is, if you know that eta is less than 1 over k, this tells you that if I look at the H1k norm, I can absorb the k squared u squared term into this. Well, where u, I should have said u, it should be u minus un on this particular guy. Okay. So when I'm looking at that data, the error, okay, I can pretend that the H1k norm, or if you like the quadratic form A, I can pretend it only sees the gradient. Okay. So in other words, this A, which is like more or less like the H1k pairing, okay, with a flipped sign, right, because it's not coercive, it becomes coercive, right? So instead of having to deal with gradient u squared minus k squared u squared, as I had in A, I can forget about this piece, morally speaking, when I'm dealing with this error. So if I want to look at the H1k squared norm of u minus un, that's comparable to A, this thing stuck into A. I do need to use something about coercivity of this exterior Dirichlet and Neumann, which is an interesting separate story. But okay, but I'm going to pretend that A is this coercive thing. It's as if I were dealing with now the Poisson equation rather than the Helmholtz at high frequency. So once you're uniformly elliptic, everything is good. Okay, by Galerkin orthogonality, I can switch out the un in the right slot for wn, something different in the Galerkin subspace, whatever I like. And then I bound this in terms of the H1k norm. I divide through by the H1k norm, and I find that u minus un in H1k is bounded by a multiple of u minus wn in H1k for any wn, and that's quasi-optimality. It's a cool argument. I really like it. I've been itching to show it to somebody.
I mean, it's really interesting how it seems like the usual standard self-adjoint argument using the coercivity in this way, but in this adjoint problem. I mean, it's
sort of about regaining coercivity, because of course the whole enemy is that A isn't coercive. I find it funny that the whole game is to show that in the H1k norm, one component isn't contributing. It does feel like maybe you could do better somehow, but I don't know how.
Yep.
I don't know how.
Do we have other questions? Well, if nobody has them, I have another one. Alexandre, you had the.
Yeah, I have my previous naive question. I don't know how the dependency on the constants on the domain are. You said they would be showing up in various subtle ways.
Well, showing up very implicitly, right? Because it's buried in part in the Escarioza-Montaner-Zheng analytic estimates. So I don't know how you carry the shape of the domain through those estimates. I suppose one could, but it would be quite tricky.
I actually, following up on that, one of the experiments that you show later on, I think, the one with the open screen.
Yeah.
Um, so, so clearly the edges of the screen, at least in the eyeball norm, they don't look like they're analytic. This does not
Oh,
look
I
like
see.
an
I just
analytic.
wanted to show you a trapping obstacle. Actually, this image was not supposed to illustrate anything too serious. Just a trapping obstacle with a wave in it. In fact, it doesn't really illustrate what I was supposed to be explaining, which is that the solution could be really quite singular, quite big inside, because you haven't tuned it to the resonant frequency. I guess it illustrates the later theorem, which is that probably you're okay uh, if you choose a
Well,
random frequency. So yeah, no, you're right. This one isn't analytic. Um, I think I've forgotten whether Malenk and Sauter have. I don't think they've done analytic corners yet, but I think you would expect it to be okay for analytic corners.
um, yeah, corners seem to introduce all kinds of
Hmm.
interesting phenomenon for high
Yeah.
frequency, right? So
Yeah. So there are. Yeah. So for purposes of this, though, we're not so worked up about the diffraction by the corners
indeed, because you're away from it, right?
we're
So
away from it. Yeah. So the interesting thing from the point of view of the shape of the obstacle from this argument is just the analyticity. And so the question is, do you have a good analytic estimate if you spectrally localize using the functional calculus for the Laplacian exterior to an analytic corner? So Malenk Sauter had done, I think, straight planar polygons
yes,
in their previous
yes,
work. I don't
yes,
think anybody's done analytic corners. Of course,
not
there,
that
I
I
mean,
know of.
there are things known by like Doge, Costabel, Nicaise about elliptic estimates with analytic corners, but we can't use the standard elliptic estimates somehow. So let me tell you a way that I initially thought we were going to prove this that doesn't work. You think I have a good elliptic estimates. If I cut off in the functional calculus of the Laplacian, I can apply any power I like of the Laplacian, and I stay in L2. Therefore, of course, I'm in every Sobolev space by elliptic estimates. Okay? And so I just write down the estimate I get. But the problem is that gives you terrible control of constants as you take more and more derivatives.
Yeah.
We've internalized, I can just trade, or at least I've internalized trading off Laplacians for other derivatives, which is fine for any fixed Sobolev space. But if you want uniform control as the power gets big, okay, and of what, d to the alpha u looks like, if I want to estimate, d to the alpha u in terms of Laplacian to the alpha over 2u plus u, I can do that. But if I use conventional elliptic estimates, the constants have terrible behavior as alpha goes to infinity. That's why the heat equation was necessary. In fact, if you think about it, these kinds of estimates would hold if I used a Schwarz cutoff rather than a compactly supported cutoff, and then I wouldn't expect analyticity. So you have to do something somehow stronger that uses the fact that the cutoff you were using in frequency space was really compactly supported. So so all those nice elliptic estimates, for example, in Costabel, Doge, and Nicaise, we can't use them. We need something more. So I don't know that anybody's done heat equation estimates in analytic corners, for instance. And if people know a reference, I'd love to know it.
Certainly, I don't remember anything in the numerical analysis literature. So
Yeah.
nice. I enjoyed your talk. Thank you.
Thank you.
Thanks, Midima. Otherwise, I see that Anders, you've unmuted yourself. Did you have a question?
No, I was just, I wanted to be prepared in case I had.
Okay. It's all right. I just wanted to make sure that if you had one, that you were properly
Oh, thank you.
asked.
So maybe I can answer Lenny's question from the outset, because I somehow didn't give a very good account of that. I think what I wanted to say was just that when I do this integration by parts, I end up with a boundary term, right, that's the derivative of u times u on the boundary of this ball, right? And that's this, right? So I'm just saying that this is the term you get by integration by parts, given that it solves the exterior problem, right? Exterior to the ball, it also satisfies this problem. You can find one of these in terms of the other. right? Since it's an outgoing solution outside the ball.
Yeah, but what I was saying that you are integrating by parts also inside of the ball. So it
Right.
looked to me that you had to get not just the exterior Dirichlet to Neumann, but the sum of the exterior and the interior.
I see. No, it's just the exterior, because all you're using
Because the exterior gives
confusing,
you
right?
the normal derivative from one side, the interior gives you the normal derivative from
Exactly.
the other
Exactly. Yeah. There's no jump.
and they have to match. So
It's a fictional interface. Exactly.
yeah.
Exactly.
So
Okay. I didn't say that very clearly. Thank you for the clarification.
okay, but
Cool.
All right, thank you for this explanation as well. I was wondering the heat equation argument. You were saying that one of the reasons why one of the hard parts or there is finding estimates for solutions to this heat equation for very small time. But I mean, this may be naive, and this is maybe me not having worked with the problem enough. But shouldn't your argument also tell you that the solution is in the range of the heat equation for a very long time after it has had time to stabilize as well? And do you get better estimates by
Well, so remember that the spectral cutoff, I said,
Uh-huh.
oh, it's low and high frequency, but the spectral cutoff is in h squared Laplacian. So there's a 1 over h squared floating, there's an h squared floating around. So
yes,
in a short time, you're taking, or in terms of k, right, you want to include the characteristic set, which is getting bigger and bigger and bigger as k gets big. So it is degenerating, and unavoidably so, I'm afraid. I wondered if you could do something with like Laplacian squared, some kind of biharmonic heat equation, or somehow soup up the heat equation to get even a little more. Because this is where we're losing relative to these optimal estimates of these other guys. But I couldn't see how to do better than the heat equation.
Yeah, I mean,
Like what's
it
more?
is true. It is true that as soon as you have a splitting and you lose more on one side than the other, you just ask yourself how can I put more of the good side in the bad
Well,
side in the good
interesting
side?
point. Maybe we should split closer to the characteristic set. Actually, that's a good idea.
Yeah.
You could do something second microlocal where you would split in an h-dependent neighborhood of the characteristic set.
Yeah, I mean
Then you would instantly lose on the h2 side. I'll have to think about that. I like that idea. It's a good point.
But the thing is, I mean, how I see usually these type of things is that if your estimate is original, you can afford to lose something on the H2 side if what you lose doesn't match on both sides. I mean, it's
Right.
a very
You're right.
it's some sort of truism in a way.
I have
but
to remember if we can afford to lose anything on the h2 side. I'm not sure we can.
I mean, maybe not to reach a cap de Bosque
Yeah.
estimate, but maybe to
Yeah.
still
No,
get a better.
It's a good idea to cut off closer to the characteristic set. That's often how to sort of optimize microlocal estimates that weren't otherwise microlocal, right? You just need to be that much closer to the characteristic set. Yeah, that's something to try. I agree.
All right. Does anyone else have? We may have time for one last question. It seems that that we've had enough questions for today. So thanks again, Jared, for the talk this week.
Thanks again for having me and for running this seminar.